So very similar to air pollution, there are point and non-point sources of water pollution. So point sources of water pollution include discharge pollution from specific locations like drain pipes, ditches, or sewer outfalls, like those that come from power plants or factories. So all of those are considered point sources. We also have non-point sources. These non-point sources have no specific location where they discharge into a particular body of water. This includes runoff from farm fields, runoff from parking lots or golf courses or lawns and gardens. So all of that combined are our non-point sources. So what are some ways that water pollution manifests? There's something that we need to talk about before we get into details, but that is biological oxygen demand. As you know, oxygen is removed from water by respiration and chemical processes that consume oxygen. So life, biology, has a demand for oxygen in the way of respiration. They need that to breathe and to metabolize. And so because oxygen is so important in water, the dissolved oxygen levels in that water are often measured to compare water quality in different places. So dissolved oxygen is shorthanded with DO, and those DO levels can be measured to compare water quality. Organic materials like sewage or paper pulp in water increase oxygen consumption because they stimulate decomposition. So those biological animals that will decompose sewage or paper, they draw down that dissolved oxygen. They scavenge it up because they are actively breaking down sewage and paper pulp that's being delivered to that water body. And so biochemical oxygen demand is the amount of dissolved oxygen consumed by those aquatic organisms. They're oftentimes aquatic microorganisms. And then you have the chemical oxygen demand, the COD, which is a measure of all organic matter in the water. So here we have a diagram from your textbook that shows this oxygen sag phenomenon. So let's break down the different components and then see what this graph is telling us. Here we have on the bottom the dissolved oxygen levels that are reported in parts per million. So in this zone here, this is considered the clean zone. This is where we have trout, perch, bass, mayfly, and stonefly and caddisfly larvae. So here we have a clean zone on the left and a clean zone on the right. We also have these in-between areas that show variable concentrations of oxygen ranging from 0 to 2 ppm and then 2 to 5 ppm. So what's happening here? It's called the decomposition zone, the septic zone, and the recovery zone. In the decomposition zone, this is where we have rough fish and leeches, those that are able to survive variable concentrations of oxygen. And then here in the septic zone, this is where we just don't have any fish. Instead of fish, we have sludge worms, we have midge and mosquito larvae. And this is where oxygen levels sag. They fall anywhere from about 0, so no oxygen being there, to as high as 2 ppm. Over here in the recovery zone, this is where we have those rough fish again. We have leeches and isopods, and that's where our oxygen begins to go back up at 2 to 5 parts per million. So what's happening here? This is caused by the release of materials that must be decomposed into a water system. Here we have in the decomposition zone, the influx of sewage coming from a source here. This seems to be a drainage pipe, and it's leaking that sewage right into this waterway. So let's take a look at what is happening to this biochemical oxygen demand. Here in the clean zone, it's at this level. And then we see that really spike up at that decomposition zone where that sewage enters our waterway. Here we have lots and lots of oxygen that's needing to be used to decompose that freshly added organic material. And then that slowly and steadily drops off into the recovery zone and then falls back to the level that it was in the first clean zone. But let's trace this black line. This black line is what's happening to dissolved oxygen. So in the clean zone here, it is really high. And then we notice that it begins to sag here. So this is that oxygen sag that is being experienced in this water body due to the elevated biochemical oxygen demand that's being experienced. So here, just beneath where the sewage is being input into the system, we see this oxygen sag, again, falling very, very low in oxygen concentrations. And then we begin to pick back up that oxygen concentration back to where it was before in another clean zone. So actually a great deal of time and distance may be required for the stream and its inhabitants to recover entirely. So what happens naturally when nutrients get put into a system? There's a difference between plant nutrients and then cultural eutrophication causing bloom events or large demand for that biological oxygen. So rivers and lakes that have clear water and low biological productivity are said to be oligotrophic. We can break this word down, as we can always do with our complicated biology and science words. Oligo means little and trophic means nutrition. So in an oligotrophic area, there's little nutrition for biological productivity. And therefore the water tends to be pretty clear. You don't have a bunch of that algal bloom or algal mats that are being stimulated by nutrients. So this water clarity is also affected by sediments, chemicals, and the abundance, again, of those planktonic organisms. Clarity is a useful measure for water quality as well as water pollution. In contrast to oligotrophic areas, you have eutrophic areas. Again, we could break down this word. Eu means true, and trophic means nutrition. So a eutrophic area is a well-nourished area. This means that they are rich in organisms and nutrients like phosphorus and nitrogen, as well as organic materials. So human activity can greatly increase the eutrophication process, making a water body more and more nourished with fertilizers, for example. This is called cultural eutrophication, and it's caused mainly by increased nutrient input into a water body that is sometimes beneficial, but also, as we noticed on the previous slide, there's that oxygen dip, that sag in oxygen when you add a whole lot of nutrients to a system. So this eutrophication process you're probably most familiar with when you take a look at a duck pond or a scummy pond in your neighborhood that's just full of those dense green algal mats. Those are called blooms of algae, or thick growths of aquatic plants that's stimulated by an addition of nutrients. So eutrophication is probably something that you've seen before, but now you understand what causes it. It's just an acceleration of nutrient input into that system. Unfortunately, this cultural eutrophication can accelerate the aging of a water body enormously over natural rates of organic and nutrient input. Lakes and reservoirs that normally might exist for hundreds or thousands of years can be filled in a matter of decades. So we have inorganic pollutants like metals, salts, and acids that can also be added to our water systems. Among the most dangerous and highly regulated are those heavy metals like cadmium, tin, and lead. And these metals are really highly persistent. They can accumulate in the food chains through bioaccumulation and biomagnification that we've talked about before, that unfortunately can affect humans if we were to fish or swim in those areas. Currently, the most widespread toxic metal contamination in North America is mercury that's released from incinerators. These incinerators are associated sometimes with coal burning power plants. And unfortunately, that makes it a pretty widespread problem in the United States. So, as a general rule, Americans are warned not to eat more than one meal of wild caught fish per week. And that's because of metal accumulation and mercury accumulation in those fish. Top marine predators like sharks, swordfish, bluefin tuna, and king mackerel, they tend to have especially high contents of mercury. So especially pregnant women or children should avoid these species entirely. Here we have a breakdown of the different types of pollutants that are found in water bodies in our area. And these include organic chemicals like pesticides, as well as industrial substances. The two principal sources of toxic organic chemicals in water are from improper disposal of industrial and household waste, and secondly, pesticide runoff from farm fields, forests, roadsides, golf courses, and private lawns. There are thousands of different natural and synthetic organic chemicals that are used in the chemical industry to make those pesticides and even plastics or pharmaceuticals. Many of those chemicals are highly toxic. That means even exposures at a very, very low dose can cause things like birth defects, genetic disorders, and cancers. And unfortunately, as we've mentioned before, some of these are persistent for a long time in the environment. And so some are worse than others. And here we have different water bodies and the county that they're located in. And it might behoove you to take a look at some of those main pollutants that are found in those water bodies. So for example, if you were thinking of doing some bass fishing in Watts Bar, make sure not to eat the striped bass because there's a whole lot of PCBs in that water reservoir. So this might make you think, okay, let me just avoid all of that and switch to bottled water. Unfortunately, if you've not already heard this, bottled water is just a huge, huge scam. Let's not even talk about the amount of wasted plastic involved in consuming bottled water. Every year, Americans buy about 28 billion bottles of water at a cost of about 15 billion, with a mistaken belief that it's safer than tap water. And it's actually not. About 1/4 or 7 billion bottles of all bottled water in the United States is simply reprocessed municipal water. The rest is simply drawn from groundwater aquifers. And so groundwater sources may or may not be safe. So in other words, when you're buying a bottle of water, you're getting just reprocessed municipal water that you could have easily gotten from your tap, or you're getting it from groundwater sources that may or may not be safe. And a recent survey of bottled water in China found that 2/3 of the samples tested had dangerous levels of toxins or pathogens. So don't always rely on bottled water being the safest. The first is sediment, and sediment is a natural part of any river system. Sediment fertilizes floodplains and creates fertile deltas, but human activities, in particular urbanization and farming, greatly increase sediment loads in rivers. Silts and sediments are considered a large source of water pollution in the US that's responsible for 40% of the impaired river miles in EPA water quality surveys. Cropland erosion contributes to 25 billion metric tons of soil, sediment, and suspended solids to world's water surfaces each year. So way back, if you remember about erosion in farmlands being a problem, well, it causes a secondary problem in delivering too much sediment and silt to water bodies. In addition to sediments, there's also thermal pollution. And this is usually effluent from cooling systems of those power plants or other industries that alter the water temperature, making it warmer. This raises the water temperatures from normal levels to something that can be adversely affecting water quality and aquatic life that needs a certain temperature of water to thrive. And so this presents persistent challenges. Not only are we dealing with those natural processes like sediment transport, but also eutrophication that is driven by runoff in urbanized areas or agricultural lands. We also have pathogens, pH changes, concentration of organic pollutants, temperature, as we just talked about, turbidity, and pesticides. All of this contribute to the persistent challenge of securing safe water. Developing countries often have serious water pollution, including parts of Russia, along with the Balkans and Central Asia. These waters in those areas remain extremely polluted. Japan, Australia, and most of Western Europe have improved substantially their surface water quality in recent years. This is a combination of sewage treatment in wealthier countries of Europe, as well as paying attention to those point sources going into water bodies. So Sweden, for instance, serves 98% of its population with at least secondary sewage treatment. And this is compared with 70% in the United States. So Sweden's doing a better job of delivering cleaner water to its people than we do here. It's estimated that in China, about 70% of the water is unsafe for human consumption, and that the water in half of the country's major rivers is so contaminated that it's unsuited for any use. So not only are we talking about consumption, but bathing, cooking, washing, all of that. Groundwater is especially hard to clean. About 1/2 of the people in the United States, including 95% of those in rural areas, they depend on those underground aquifers for their drinking water. These aquifers, these underground aquifers, are vital resources that are threatened in many areas by overuse, as we discussed in previous slides, and pollution, as well as a wide variety of industrial, agricultural, and domestic uses. The EPA estimates that 1.2 trillion gallons of contaminated water seep into the ground in the United States. And so when that deep aquifer is contaminated, it's very, very hard to clean it up because, of course, you have to pump it to the surface, you have to clean it, and then you have to pump it back into that aquifer. So what are some sources of groundwater pollution? We have in this diagram illustrated a couple here. So we have our deep aquifer, we have our shallow aquifer that's being separated here by an impervious layer of rock. And then on land, we have all of these different processes that are adding to contamination of this aquifer. So first we have fractures in some impervious layers that allow leaking materials to go into the soil and eventually make it to shallow aquifers. Also in those shallow aquifers, we have industrial waste that's being run off into the shallow aquifer, as well as some things that might be injected directly either into the shallow or the deep aquifer here. Most of these you'll see are passively injected, like surface runoff or in leaking materials or leaking septic tanks. All of those non-point sources contribute to contamination of both shallow and deep aquifers. So this is groundwater pollution, meaning water that's on land. If you remember back to the top of this lecture, we discussed that the ocean is the largest reservoir of water on our planet. The ocean has very few controls on pollution. This includes coastal bays, estuaries, shoals, and reefs. Often these are the most overwhelmed by pollution. These lead to things like dead zones where there's just no oxygen available at all for life that drastically decreases the biodiversity. Or this could manifest in poisonous algal blooms that have toxins that can be easily spread to other areas. In addition, you have toxic chemicals, heavy metals, oil, sediment. All of those affect some of the most attractive and productive oceanic regions on our planet, unfortunately. Another thing to consider as far as ocean pollution is discarded plastic. Discarded plastic, flotsam, and jetsam are becoming a ubiquitous mark of human impact in the ocean. There's 6 million metric tons of plastic that are tossed from ships each and every year. It's extremely unnerving, and we're going to watch a documentary called A Plastic Ocean about this soon. But researchers have recently discovered that a vast swath of the Pacific Ocean is filled with a soup of plastic garbage. This has gained a special name called the Great Pacific Garbage Patch. And this garbage patch is slowly swirling, and it fills up 2 convergent zones in the Pacific Ocean. So in these convergent zones, it's collecting trash literally from all over the world and piling it into these gyres. One of these patches is larger than the state of Texas. It's very, very hard to imagine this. So I've posted a link for an article for you to read on the tartan. So what are some avenues that we have for water treatment and remediation? Well, the cheapest and most effective way to reduce pollution is to stop producing the pollution, or at least stop releasing it into those waterways that we rely on. Eliminating lead from gasoline has resulted in a widespread and significant decrease in the amount of lead in US surface waters, which is really, really great. So careful handling of oil and petroleum products can actually also greatly reduce the amount of water pollution caused by those materials. And industry can reduce pollution by recycling or reclaiming materials that otherwise might be discarded in the waste stream. And this is probably also beneficial for those companies because they can extract valuable metals and chemicals and then sell them instead of releasing them back into the water system. So in this way, it's definitely a win-win. We've brought up this term before, municipal, in the way of water. So how do we get municipal water? Well, we have to treat municipal waste in order to get municipal water. So under natural conditions, water purification occurs constantly in soils and water. And the high population densities of cities produce much more waste than natural systems can process. So in rural areas, it might be a lot easier to rely on natural processes to clean water than in an urbanized area. In these urban centers, we have to more and more rely on municipal waste treatment centers. So most developed countries require cities and towns to build those water treatment systems to purify human and household waste. Most rural households, they use septic systems, which allow solids to settle inside of a tank where bacteria can decompose them. So under natural conditions, we have natural processes like sand and soil that filters water, but we can learn something from nature and apply those techniques that are normally done in nature and use them to treat our municipal waste. And you'll see what I'm alluding to in a video, but for now, let's talk about the steps in municipal treatment. There are 3 levels of quality, and these are all overseen by sanitary engineers. They've developed ingenious and effective municipal wastewater treatment systems. Primary treatment physically separates large solids from the waste stream with screens and settling tanks. Beyond primary treatment, there's secondary treatment that uses aerobic bacteria to break down dissolved organic compounds. So although the wastewater is usually free of pathogens and organic material after the second treatment, it still contains high levels of these inorganic nutrients. So if discharged into surface waters, these nutrients would then stimulate algal blooms and cause eutrophication. So we don't want that to stop at the secondary treatment phase. We move into tertiary treatment, which removes metals and nutrients, especially those nitrates and phosphates that act to stimulate those algal blooms. Sewage sludge can be a valuable fertilizer, as we saw with the oxygen sag diagram, but it could be unsafe if it contains metals and toxic chemicals. Some cities will spread this sludge on farms and forest lands, while others convert it to methane or natural gas. So again, it's a win-win in terms of treating our water through these municipal treatment plants. So as I mentioned previously, we have a YouTube video that will help explain how we can use soils and sediments and trappings of different sizes to our benefit in our wastewater treatment plant. So please watch this YouTube video that's posted on the tartan. However, despite all of those multi-tiers of treatments and different materials and stages overseen by those septic engineers, not all pollutants are caught in the end. In 2002, the USGS, or the United States Geological Survey, released the first ever study of pharmaceuticals and hormones in streams. And so they sampled 130 streams for 95 contaminants. And these contaminants included things like antibiotics, natural and synthetic hormones that you might have in birth control, for example, detergents, plasticizers, insecticides, and retardants. And so what they found is that all of these substances were found in low concentrations. Now, what's baffling about this is that drinking water standards only exist for 14 out of the 95 contaminants that they sampled for. And yet, they found all 95 in low concentrations. So scientists are still studying the possible impacts of these contaminants for our health and the environment. And here we have a breakdown of those different unusual pollutants like steroids or non-prescription drugs within surface waters. And here we have the detection frequency represented in the percentage of samples. And if you're curious, our antibiotics, those come mostly from things like antibiotic soaps and body washes and things that unnecessarily, in my opinion, have antibiotics in them. There are alternative waste treatment systems that do exist. Many contaminants actually have tons of energy that can be harnessed for different purposes. Remember, we talked about sewage sludge being used to be converted into natural gas or methane. An example of an alternative waste treatment system is this living machine that's located in Cedar Grove Cheese Factory in southern Wisconsin. This living machine is a sequence of tanks, bacteria, algae, and small artificial wetlands that convert factory effluent to nearly pure water and vegetation. This entire system removes about 99% of the biological oxygen demand, 98% of suspended solids, 93% of nitrogen, and 57% of phosphorus. So we don't always have to rely on our municipal systems. There are, in some cases, alternatives that can be harnessed. We can also remediate those contaminated ecosystems through contaminant extraction or biological treatment. Oftentimes, we can harness the power of living organisms to clean contaminated water. This is called bioremediation. So we're remediating or getting back to a healthy state, that water body, through biological processes. There's restored wetlands, for instance, along stream banks or lake margins that can effectively filter out sediment and remove pollutants. And then finally, some plants are very efficient at taking up heavy metals and organic contaminants. So bioremediation in this way offers exciting and inexpensive alternatives to conventional cleanup. So just as there are many sources of water contamination, there are many ways to clean it up. And here's a table of some important water quality legislation that helps you see how we've tried to tackle the problem of water contamination through time. The most important of these is the 1972 Clean Water Act that protects water in the United States. It established a national pollution drainage elimination system, which requires an easily revoked permit for any industry, municipality, or other entity dumping waste in surface waters. For point sources, the Act requires discharge permits and the use of best practicable control technology. It requires disclosure of what's being dumped, and it gives regulators valuable data and evidence for litigation. Perhaps the most important result of this act has been the investment of $54 billion in federal funds and more than $128 billion in state and local funds for municipal sewage treatment facilities. So all in all, the Clean Water Act was ambitious, powerful, bipartisan, and largely successful. It made clean water a national priority. And so along with the Endangered Species Act and the Clean Air Act, this is one of the most significant and effective pieces of environmental legislation ever passed by the US Congress. The ambitious goals within the Clean Water Act was to return the US surface waters to fishable and swimmable conditions. So there are areas of progress, which is a great thing to look to how to model our behavior and future legislation. So as a consequence of the 1972 Clean Water Act, only 10% of our water pollution now comes from industrial and municipal point sources. One of the biggest improvements, thankfully, has been in sewage treatment. Nearly everyone in urban areas is now served by municipal sewage systems, and no major city discharges raw sewage into a river or lake. That's great. We're no longer dumping raw sewage into our water bodies. So to conclude, water, of course, is a precious resource. And as the human population continues to grow, water is likely to become even more and more scarce and more valuable in the future. This might bring about water wars as people discuss water rights. The US federal, state, and local pollution controls have greatly improved our water quality in most places. And in rapidly developing countries like India and China, water pollution is still a serious threat. Constructed wetlands for ecological sewage treatment provide low-tech, inexpensive ways to reduce pollution and maybe turn some of that sewage into alternative energy sources.